Hey there. In class today, I was talking about sigma notation and how we use it, how we deploy and use some of the properties of sigma notation. And one of the examples I gave was, or two actually, was how we use sigma notation to help us solve the area problem. I gave kind of a sophisticated example, and at one point, I pulled in an equation out of nowhere to use. And at the end of class, Alec asked, "Where did that equation come from?" So I thought I'd just take a minute to create a little screencast to show you all where that equation came from. So here's the area we're trying to work with. So it was the graph of y equals x squared on the interval from 0 to 3. Okay. And basically what I'm gonna did was this. I let n be the number of sub intervals of 0, 3 we use. And remember, we're going to use subintervals of equal width. So the width of those subintervals is going to be 3 over n. And then I'm going to define a sub a of n. It's going to be a function, and it's a function that takes n as an independent variable as an input and outputs the area of n approximating rectangles. And the idea is this. If A, without any n, if A equals the area under y equals x squared on the interval from 0 to 3, then A is approximately equal to AN. And also, as n grows, AN gets closer to A. In fact, the limit as n goes to infinity of AN is going to be equal to A. So this is the idea behind the work we did in class today, April 27th. So let me show you how I worked up this function, or an expression for AN. So that's what I'm going to do, is I'm going to show you a formula for AN. So let's just draw a picture. So my graph of y equals x squared looks like this. We're in the interval from 0 to 3. So what's going to happen is I'm going to have n rectangles. So that means I need n subintervals of 0 to 3 of equal width. And that width is going to be delta x, and as I remarked above, that delta x is going to be 3 over n. So when I do that, I'm going to, let's say, let x of I be the endpoint ith endpoint of the subintervals. So we'll be chopping up the interval from 0 to 3, and we'll get a bunch of these endpoints of the subintervals. Okay, and the intervals we're going to have, or the subinterval endpoints, are going to start at x0, then we'll have x1, x2, x3, all the way up to xn. All right. So the ith subinterval is going to be x sub I minus 1 to x sub I. So we'll have the first subinterval, the second subinterval, the third subinterval, and so on and so forth up until the nth subinterval. Okay, so our I is going to go from 1 up to n. Okay, Let me turn the page. So what I want to do is I'm going to say let A sub I be the area of the ith rectangle. Okay, where I goes from 1 to n, just like the subintervals from the previous page. So the area of the ith rectangle is going to be its width times the height of the ith rectangle. Okay. Now the widths are all going to be the same. That's going to be 3 over n. But let me do a quick sketch. It'll just be a cartoon of our situation. So here's our graph. So suppose I'm on the ith rectangle, and these are the endpoints, xi minus 1 to xi. Then you can see here is the area in orange that I want to compute. I want to compute that area. But what I'm going to use to approximate that area is this rectangle. So its width is going to be delta x, and its height here is going to be the height of this point here on the line, which is right here, which is going to be xi squared, right? Because the function is y equals x squared. So I plug in my x value here to get the point on the graph above it. The y value is xi squared, so that's the height, xi squared. Maybe I should do that in green. Okay, so let's go back up here, continue this formula. The width is delta x, the height is xi squared. So I'm going to do xi squared times 3 over n. Now we can find a formula for xi. Okay, so we'll pause this calculation to ask what is xi. And so if this is the interval from 0 to 3, this here, that's x0. And the next endpoint is x1. And this distance here is delta x. So x1 must be delta x. And then the next endpoint is x2. This distance here is delta x. So x2 must be 2 delta x. And likewise here, x3, that's going to be 3 delta x. And that continues. And so this last one out here, 3 is going to be n delta x. And you could check that. Delta x is 3 over n. N's cancel and you get 3. So nice internal consistency there. But what I want to point out here is we've just discovered this formula for xi. Xi is I times delta x. So let's continue this formula down here. So xi squared, that's I delta x squared. And delta x is 3 over n. So that's I 3 over n squared. 3 over n. So that's I squared 3 over n cubed. Okay, so that's the formula for AI. Let's continue that here. We'll make a note. AI is I squared times 3 over n cubed. So A sub n, the area that we get when we subdivide our region into n subintervals of equal width and build rectangles on top of them, that's the sum of the area of the rectangles. And we know the sum is I squared times 3 over n cubed. That's just work that we just did. And now I want to calculate this. So what I want to point out to you is this expression here, 3 over n quantity cubed, doesn't have an index in it, does not have an I. So for all intents and purposes, well, if you wrote out this summation, every term would have a 3 over n to the third power in it. So I can factor that out. Use a property of summations and factor that out. And I get this. And then here I can use one of my summation identities and apply it to this. The summation identity tells me that this is equal to n times n plus 1 times 2n plus 1 over 6. This isn't something you have to memorize, but you have to be able to recognize that we know a formula for this, and then when it's time to use it, find it. And that's what we're doing right now. So the summation identity lets me replace the summation with n times n plus 1 times 2n plus 1 over 6. Right? So that's my formula for an. So let's just take this one more step. I can't remember where I left it in class today, but this is 3 cubed over 6 times n plus 1 times 2n plus 1 over n cubed. And 3 cubed is 3 times 3, which is 9, times 3 is 27, so this is 27 sixths. And this over here, how do I simplify this? N squared plus n times 2n plus 1. That's the first step. The second step is multiply this out, and what do I get? I get 2n cubed plus 3n squared plus n all over n cubed. Same mistake here, that should be 27. So 27 sixths times 2 plus 3 over n plus 1 over n squared. All right, and as n goes to infinity, today we saw that this goes to 54 over 6, which is 9. Right? And that's the area under that curve. So this fills in that gap that I left in lecture today. You don't need to be able to do this now. It's kind of fun to be able to do. But this answers the question that Alec asked, where does that come from? Here you go. See you next time.